In this video, I'm going to talk about yet another result that has an amazing short proof that just came as a huge surprise when it was discovered. It was actually very recent, just over a year ago. And it solved a problem in theoretical computer science that I'm not actually going to talk about, called the sensitivity conjecture. The sensitivity conjecture had been reduced to a very nice combinatorial problem. And that problem also seemed hard until Hao Huang solved it completely. And so it's his proof, or rather, not quite exactly his proof, because this was a very surprising thing, but he came up with a proof that staggered people by its simplicity. And then a very well-known theoretical computer scientist called Scott Aronson, who has an absolutely wonderful blog, blogged about it. And somebody in one of the comments pointed out that Huang's argument could be made even simpler. So it was a bit like the situation with the solution of the Knaser conjecture, where Imre Birani came up with a really simple proof, and it turned out not to be as simple as you could get. So Huang's proof was wonderfully simple. The proof I'm going to give is basically Huang's, but it just at a certain point, it turns out that one of his steps can be done even more easily than he did it. So what is the combinatorial problem that I'm going to talk about? It concerns the following question. What is the minimum degree? I'm going to make the question more specific, but I'll ask a sort of more general question. There's a minimum, sorry, I don't mean a minimum degree, the minimum possible maximum degree. Sort of minimax type thing of an induced subgraph of the hypercube. That's I just call it the cube. It's the n-dimensional cube Qn. So that is 0, 1 to the n with x and y joined. We've met this earlier on in the course. If they differ in exactly one coordinate. So given any vector x, if you flip one of its coordinates, you get a neighbor. So each point in Qn has exactly n neighbors. And I would say so with a given number of vertices. So that's not exactly the question that we're going to talk about, but it's a generalization of the question. But let's just make a couple of remarks about this. The cube is a bipartite graph because if you have two vectors and the number of ones has the same parity, then they're not joined by an edge, because every time you change one coordinate, the parity of the number of ones changes. So split is a very important fact about the cube. Simple fact, but or if you like to think of the hypercube in an equivalent way as the power set of the numbers from 1 to n, in other words, all subsets of the set 1 up to n, then we're splitting sets. So then two sets are joined if you can get from one to the other by removing or adding exactly one element. And so then we split according to the parity of the cardinality of the sets. So what does that imply about induced subgraphs? So an induced subgraph with fewer than 2 to the n minus 1 vertices, or up, can have no edges. I see now that the English language is slightly ambiguous here. So that means it is possible for it to have no edges. It doesn't mean it cannot have edges. Obviously it can have edges, but it doesn't have to have any edges. So the answer is 0 if the number of vertices is smaller than or equal to 2 to the n minus 1. So the first interesting case is, what if you have 2 to the n minus 1 plus 1 vertices? And this is exactly the question that turned out to be important in theoretical computer science, because the conjectured answer would solve the sensitivity conjecture. And it's this that Huang managed to determine. So a quick remark here is that if you do take all sequences from one half of the bipartition, then when you add a vertex, it's going to be joined. So if you take, say, all sequences with an even number of ones, and if you take any sequence with an odd number of ones and add it on, it'll be joined. All its neighbors will have an even number of ones, and so you'll have a vertex of degree n. So so that gives us an example. That gives us nothing at all, because the maximum degree in the entirety of Qn is n. So we can ask, can we do a bit better than that? And it turns out that there is an example discovered by, if I can remember, Chung, Füredi, Graham, and Seymour, of a graph, or in other words, a set of an induced subgraph of Qn, or equivalently a set of vertices of 2n minus 1 plus 1, 2 to the n minus 1 plus 1 vertices, where the maximum degree is, so an example, and I'm going to write delta for the maximum degree. Delta is square root of n. So quite a lot smaller than the trivial upper bound of n. And they also showed, this was their main result, they showed delta is greater than or equal to something around log n. So I think it was something like log n minus log n plus 1. That may not be the exact formula, but anyway, it's so I'll put that with a, so that it's something that looked a little bit like that, but it's let's put instead, I'll do something I like to do, which is put greater than roughly log n. But what Huang did was obtain a lower bound for of root n, which therefore shows that this example is best possible. Now, before I present his example in full, I want to talk a little bit about the relationship between adjacency matrices and graphs, and a nice way of thinking about linear maps. So supposing we have a graph something like that, and we take its adjacency matrix. So if I've labeled the vertices 1, actually I won't write down the adjacency matrix, but what I would do if I did would be to label the vertices 1 to 5 in this particular example, and then in the sort of ijth place, if there's an edge joining vertex I to vertex j, I put a 1, and if there isn't an edge, I put a 0. And what I'd like to do is think, so that adjacency matrix will define for me a linear map that takes vectors in R5 to vectors in R5. And what I'd like to do is to have a way of thinking about that linear map in terms of the graph rather than in terms of the matrix. So what is a vector in R5 in this picture? It's just some numbers. So we might have sort of, let's call it V1, V2, V3, V4, V5. And then what does the adjacency matrix do to this vector? So let me just draw the graph again. So what I want to do now is write down what the new vector will be when we've applied this linear map. So what we do is we look at V1 and we'll say, somewhere down here we've got a column vector V1 up to V5. And listed here, we're going to have a 1 for every neighbor. In this row, we'll have a 1 for every neighbor of V1. Sorry, V1 is the vector rather than the name of the vertex. So we'll have a 1 for every neighbor of vertex 1, and a 0 for every non-neighbor. So we'll have a 1 in the second place, and a 1 in the fifth place, and zeros in the third and fourth place. So let's just write in that particular row and just see what happens. So we had 1 in the second place, and 1 in the fifth place, and then there's the rest of the matrix, and more zeros and ones. So what's going to be in the first coordinate? Well, we'll get a V2 and a V5. So this will become V2 plus V5. And in general, what we do is we just take each vertex, look at the numbers on its neighbors and add them together. So V2 will give us, we'll have V1 plus V3 plus V5. I might as well write all these down. So V2 plus V4. And this one will be V3 plus V5. And this one is going to be V1 plus V2 plus V4. I haven't done anything very drastic mathematically, but I'm just saying that if you've got a graph, you can use it to define a linear map, and you can do it directly rather than going via the adjacency matrix. You can just say, my linear map is going to be the following. Given a vector, i.e. a function from the vertices to the reals, I'll replace the value at each vertex by the sum of the values of the neighbors of the vertex. And then the next thing I want to mention is that we can also represent a more general matrix in a graph theoretic way by just putting weights on the edges. So if I don't want to have a 0, 1 matrix, I can just, so supposing I wanted this 1 to be instead a half. So that corresponds to the edge joining V1 to V2. So I'd stick a weight of a half on that edge. And now what that would tell me is that instead of taking the sum V5 plus V2, I'd take the sum V, so I've got a weight of 1 here. I take V5 plus a half of V2, and I take half of V2 because I've got a half on the edge that joins V1 to V2. And so then instead of having this V2 plus V5, I'd have half V2 plus V5. Just not to be too confusing, I'm going to turn that back into a 1 again. But I just want to say that the whole thing is very straightforwardly generalizable to weighted graphs from graphs. And that's a remark that we're going to need. Now let me prove a very simple lemma, which is that if A is the adjacency matrix of a graph, then I've already introduced delta for the maximum degree, then and lambda is an eigenvalue of A, then lambda is less than or equal to, that's not what I wanted to say, lambda is less than or equal, so modulus of lambda is less than or equal to the maximum degree. Now, I'm going to sketch a proof without writing anything down, and then I'll give a different proof, which will be more algebraic. So the geometrical proof will be, supposing I've got an eigenvector. Let's just suppose, for example, this is an eigenvector. Let's look for the maximum modulus of a coordinate. So perhaps we could say V5 is the maximum. Then we know that V5 is going to go to lambda V5, but it's also going to go to something that's smaller than its modulus. Well, it's going to be equal to V1 plus V2 plus V4, but all of those have modulus that are smaller than the modulus of V5. So in total, when you add them together, you're going to get something that's at most 3 times the size of V5 in modulus, which proves that the eigenvalue must have been at most 3 in modulus. So we just see that because there were only 3 things we added together and they were all smaller than V5 because I went for the maximum one. And I know that it ends up being lambda times V5. That shows that lambda must be at most the maximum degree. Let's do it a different way. So proof, we get, we'll look at the L1 norm. So instead of looking at the infinity norm, which we before looked at the maximum value, I'm going to look instead at the L1 norm. So AV1, that equals the sum over all I of the sum j, aij, vj, which is less than or equal to, by the triangle inequality, sum I, sum j. Oh, I wanted to say something slightly more general. Well, I'll say what I'm saying here for the moment. So, and then I'll comment about how I can generalize it. So, aij times the modulus of vj. And now we just interchange the order of summation. So that's the sum over all j, modulus of vj, times the sum over I, aij. But this thing here, so this is non-negative, and this is just the degree of the vertex I, so it's less than or equal to delta. So the whole thing is going to be at most delta times this sum, but that sum is just V1. So if V is an eigenvector, we know that the L1 norm of AV is exactly lambda times the L1 norm of V. So that tells us that lambda is at most delta. But the extra comment I wanted to make was this proof works if A is any matrix such that aij less than or equal to 1 when ij is an edge and aij equals 0 when ij is not an edge. It's just because to have a look at this proof, I could have put here a modulus sign. So I'll just add that in. So the triangle inequality will tell me that this thing here is at most this thing here with the modulus signs in there. And then I have to put a modulus sign in here. And then the sum of these is still at most delta because you've got at most delta things that you're summing together and they all have size at most 1. So the proof just carries through even if A is a matrix that has entries at most 1 instead of exactly 1, at most, or between -1 and 1 instead of exactly 1. And actually we're going to apply this in the case where A is a matrix that takes, where on each edge of a particular graph, and it is 1 or -1. So going back to here, that will correspond to a situation where the weights that I put on these edges will be either 1 or -1. Okay, well, I'm actually going to define a matrix on Qn itself. So we're going to define Okay, I'm going to do this in a couple of ways. So the first way is I'm going to actually define it as a matrix because that actually looks rather simpler. So we'll define, what shall I call it? Well, I'll call it A naught. Let that be the 1 by 1 matrix that just has a 0. And then for each k, let ak, actually we'll call it n. Let an be the matrix an minus 1 identity, identity minus an minus 1. So this should remind you of the construction of Walsh matrices in the section on when I talked about Hadamard matrices. But this is not a Hadamard matrix because these identity matrices, of course, have lots of zeros in them. Let's just have a quick look at what the first few look like. So the first one is just that. The second one is going to be 0, 1, 1, 0. And then the next one will be 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, and minus 1, 0, 0, minus 1. Which is not doing what I expected it to do at all, which suggests that I may have made a slip. Okay, so a little mini crisis there, and I realized that I did indeed make just a tiny little mistake rather than a big mistake, which is a relief. What did I do? I accidentally wrote minus an minus 1 wrongly, as you may well have noticed, but when you're doing these things in real time, it's sometimes hard to spot it. So let's just write that in properly. It should have been 0, minus 1, minus 1, 0. Now I want to point something out about this matrix, which is if you look at any two rows of it, they are orthogonal to each other. So this one is obviously orthogonal to, the first two are obviously orthogonal to each other because they're disjointly supported. But the first row is orthogonal to the last row and the second row orthogonal to the third row. And let's just, so I think I won't bother to write down another one, but I would just take this matrix, put it here, and then put an identity, and minus that matrix, and get an 8 by 8 matrix for the next one. Let's just quickly see why it's orthogonal. That's easily proved by induction, and the proof is rather similar to the proof for Hadamard matrices. So if I take two rows that are in the same half, then by induction, those two rows of an minus 1 are going to be orthogonal to each other, and the two rows of the identity matrix are obviously orthogonal to each other because they're disjointly supported. If I take two rows in different halves, so supposing I take the ith row here and the jth row here, then I'm taking the ith row of an minus 1 inner producting with the jth row of the identity, and here I'm taking the ith row of the identity and taking its inner product with the jth row of an minus 1, but subtracting. And because an is a symmetric matrix, so let's just quickly see what we get. We get what happens when I take the inner product of the ith row of a matrix A with the jth row of the identity. I'll just get A ij. And so here I'll be doing the same thing, but it'll be AJI, where A is an minus 1. So that'll give me 0. It's symmetric by induction as well. So this is symmetric, and we've put the same thing in the top part and the bottom part, top right and bottom left. So a simple inductive argument shows that the rows of AN are orthogonal and AN is symmetric. From that we get that AN squared is AN times AN transpose, and AN transpose evaluated at ij is the inner product of the ith row with the jth row. And because the rows are orthogonal, that's going to give us 0 if I doesn't equal j. And if I does equal j, we get the ith row of AN inner product with itself. Now, one other thing I didn't say is how many non-zero entries are there in AN? The answer is there are n. So there was 0 in A0, 1 in A1, and then each time you, so I've got n minus 1 non-zero entries here, and I've got an extra non-zero entry in each row from adding this I there. So we get n there if I does equal j. So in other words, so actually this is, strictly speaking, what I've written here is grammatically incorrect. So this is the ijth entry of AN transpose rather than the matrix AN transpose, of course. So let's now write something that is correct. AN transpose is n times the identity. That's 2 to the n by 2 to the n identity. Now, what does that tell us about the eigenvalues of AN? First of all, AN is a symmetric matrix, so it's got n real eigenvalues up to multiplicity. So, but if the square is the identity, then every eigenvalue has to be, or n times identity, every eigenvalue has to be plus or minus the square root of n, because if I take a vector of eigenvalue lambda and I apply AN twice, I'll get lambda squared times that vector, and it's got to be n times that vector. So therefore, every eigenvalue of AN is plus or minus the square root of n. Now, what can we say about the multiplicity of these eigenvalues? Actually, we can say exactly what it is by a very, very simple observation, which is another inductive argument shows that the trace of AN is 0, just because, well, if the trace of this is 0, we got, I mean, actually it's just got zeros down the diagonal. So this has got zeros down the diagonal, that's got zeros down the diagonal, so AN has got zeros down the diagonal by induction. So since trace of AN equals 0, the multiplicity of each eigenvalue is 2 to the n minus 1. I'm now feeling slightly remiss that I haven't talked about, and I do may have picked this up for yourself, but I haven't really talked about why I'm bothering to think about eigenvalues of AN. And the answer is that AN is going to turn out to be a set of weights on the adjacency matrix of the cube of dimension n. And if you remember that we showed that any eigenvalue is at most the maximum degree. So what we're actually going to try to do is take our induced subgraph, look at the restriction of the adjacency matrix of the, well, restriction of this funny matrix that we've constructed to that subgraph, and prove that we've got an eigenvalue of at least root n, or exactly square root of n, in that subgraph. And that will give us at the minimum degree. is at least the square root of n as desired. So we're going. This is another example throughout the course, and this is something I've only really been kind of consciously noticing more recently. But there is actually a running thread that goes through the course, which is that quite often in combinatorics, so sometimes in combinatorics you want to count something or estimate how big something is, and you just dive in and do it very, very directly. But also quite often what you do is you try to do it by looking at something else. You try and bound the thing you're trying to count by looking at something else. So we did it by looking at the entropy of a probability distribution supported on a set, for example. And here we're doing it by looking at a particular eigenvalue that sort of lives in an appropriate place, and that will tell us that the minimum degree is, the maximum degree is reasonably big. Okay, before I get on to that, let's just see why this matrix AN is actually related to the adjacency matrix of the cube. So supposing I take a cube, I'll start with a cube of dimension 0. What's its adjacency matrix? It's just 0. Now what if I take a cube of dimension 1? What's its adjacency matrix? Well, I've now got 2 vertices. So that's not joined to itself. That's not joined to itself. But they are joined to each other. So first vertex joined to the second vertex joined to the first vertex. Now, what do I do to create a 2-dimensional cube? I'll create a copy of this thing, and then I'll join corresponding vertices by edges. So I have a copy of the top 1-dimensional cube, and another copy of the 1-dimensional cube. And then these edges that join top vertices to bottom vertices, so if that's sort of vertex 1, vertex 2, then I've got vertex 1 prime, vertex 2 prime. So I have to do that. I'm putting in a little identity matrix. And in general, I mean, if I want to get from an n-dimensional cube to an n+1-dimensional cube, what I'll do is I'll I'll call it Bn. We'll have Bn equals an n-1-dimensional cube and another n-1-dimensional cube, and then edges that join corresponding vertices. So what am I getting? I'm getting exactly the matrix that I got here, except that all the -1s are now 1s. And so what does that tell us? It tells us that these ANs are in fact just putting ±1 weights on the adjacency matrix of the cube Qn. And we can even sort of say, in terms of, if we don't want to think about matrices, we can say what it is by looking at cubes. So what we do is we say, supposing I've put some weights on the n-dimensional cube, and I'll take another n-dimensional cube, and I'll put minus whatever weights I had onto this one, and then I'll join the corresponding vertices to turn it into an n+1 dimensional cube. Was this n-1 dimensional? So this is n-1 dimensional with some weights. I put minus those same weights, and then I join with some edges going across. Now, you'll also notice that actually any 2 rows of this matrix either are disjoint, that corresponds to 2 vertices whose neighborhoods are disjoint, or they intersect in a set of size 2. So if I have 2 vertices of the cube, that corresponds to, if you think about it a little bit, you'll see that if they're 2 apart, there's going to be only 2 ways of getting from one to the other by changing one coordinate. So in order for the rows to be orthogonal, whenever you've got them intersecting in exactly 2, you've got to have an odd number of minuses around. So what that says in graph terms is that we've got a weighting on the cubes such that whenever you've got a little square somewhere, you've either got 3 1s and a -1, or you've got 3 -1s and a 1. Actually, I'm rather familiar with this matrix. I'll just mention this because a long time ago, I wrote a paper constructing an n-dimensional normed space with two non-equivalent symmetric bases. I won't bother to say exactly what that means, but it turned out that I needed precisely this family of matrices AN in order to do that. So that made me particularly interested that it came up in Huang's argument. I've been sort of spinning things out. Let me now just finish off the argument. So let's take a set X in, well, in 0, 1 to the n of size 2 to the n minus 1 plus 1. And we'd like to prove that the maximum degree is reasonably large. So of the induced subgraph, was the subgraph induced by X. So what we're going to observe is, let's just think about what the adjacency matrix of the induced subgraph is. So let Px be the projection to X. So in other words, if I've got a function defined on the whole of the cube, Px of the function is just the restriction of that function to X. Now I want to note that the dimension of the space of functions from X to R is 2 to the n minus 1 plus 1. But the eigenspaces have dimension 2 to the n minus 1, as we saw before, because root n has multiplicity 2 to the n minus 1, and so does minus root n. And therefore, there is an eigenvector of this matrix AN supported in X. In other words, all its non-zero coordinates live in X. So let's call it V. And then we get that AN of V is AN of Px of V. That's because V is supported in X, so when you project it to X, you don't change anything at all. Because it's an eigenvector, it goes to a multiple of itself, so it's still supported in X, and so we can apply the projection again. So that tells us V is an eigenvector of Px A n Px. But what is Pn A Px? It's just taking the matrix of AN, and then we're taking out the rows that belong to X and the columns that belong to X, and just restricting to those, and applying that. So we're taking some square matrix that it corresponds to its rows and columns that correspond to the elements of X. Or in other words, this matrix here lives, all its non-zero elements live in the induced subgraph. All the non-zero entries of Px, AN, Px are weights, also plus minus 1 weights on edges of the induced subgraph. So max degree in the subgraph is at least the modulus of the eigenvalue, and we are done. maybe I'll have to let's be consistent. I'll put a little square. So that finishes off the proof. And well, it's, I think, an absolutely gorgeous argument. And I just want to stress this problem was open for a matter of decades. And so it really was a big, big surprise that it could have a proof quite as short and simple as this. And with that, I shall stop.